Okay, well, everybody, thank you for coming. As the topic says, I'm going to talk about modeling bipartite networks from available data. Now, actually, I won't actually get to the bipartite networks until pretty late in the talk, well, because I need to talk about the framework in which we're going to do this and how we're going to take the data and make use of it, and then transfer that, see how we can transfer that experience to bipartite network models. Okay, so first, a word on modeling first. So there's sort of two main approaches in modeling is sort of in contrast to sort of a more direct approach, such as what Vittoria Colizza presented the other day, where basically you reconstruct a synthetic population from the available data and then you simulate the spread over the network, right? That's sort of one empirical approach. Model-based approach, it takes a different tack, right? First, we sort of abstract key features of the network. We ask, okay, which features of the network are actually important? Which mixing matrices, which degree distributions? There can be many of them. Hopefully, they're not self-contradictory, mutually exclusive. Then we take a generative model, we estimate a generative model, a probability model for these features given the observed data. And that may not be straightforward, but that's what part of the talk is about. Then we can simulate plausible networks from the estimated model because it's generative, and then we simulate the spread over the plausible networks. And the nice thing about that is that since we get to simulate plausible networks, we get a range of predictions. We get some idea of how robust our predictions are. So getting generative models can be challenging. In particular, one challenge is the exogenous versus endogenous effect. So this network, one might say it has an excess of triangles. That is, friend of a friend is a friend. Now, I won't get into details of how you can evaluate this, but we can say that sort of relative to having no triangle effect or friend of a friend is a friend effect, this network has a lot of triangles, like 99th percentile. But it turns out that actually it's not the sort of the endogenous friend of a friend is a friend effect. Turns out that actually there are groups in this network and there's homophily within groups. And after you control for that, it turns out that all those triangles are very well accounted for. In fact, it's pretty typical, right? So exogenous effects versus endogenous effects, and we need to be able to do both. So we're going to do both in the statistical framework called ERGM. Now, Sam Jeunesse talked a bit about it in his talk, but I'll elaborate on some aspects of it. So how do we model a network in general, right? If you have these binary relations, yeah, tie, no tie, right? Well, we have to write down a model for the ties, right? For the ties, but we also have to write down the model for the non-ties or any ties that could possibly happen because there's information in that as well. Right, so we write down the model, and it makes sense to use something like a logistic regression, right? So where I say logit of the probability of a tie between I and J, is some theta1 parameter, which might be the intercept or the overall density, plus theta2 times, and maybe for this particular network, we'll say an indicator of whether I and J are in the same group, right? They're both blue, or they're both red, or they're both green, right? So that makes sense. That's pretty straightforward for exogenous effects. But then we have endogenous effects, and there, well, maybe we want to model the effects of having a friend of a friend be a friend, having a friend of a friend, right? And we might model that by counting the number of triangles formed by I and J in some third party K, right? But now we have a problem because now we have a network on the left-hand side and we have a network on the right-hand side, right? So it's kind of autoregressive almost. And so the idea behind ERGMs resolve this by saying that let's write down the regression in terms of summary statistics. So we have our theta1, which we want to use to model overall tendency to have ties. So let's have a summary statistic, total number of ties in the network. And maybe theta2, remember that was representing the tendency to have homophilous ties. So let's count the ties within groups. And for triangles, we want to use that to model the tendency of a friend to be a friend. So let's count the number of triangles in the network. Now, as a very brief aside, normally I'm using triangles illustratively because everybody knows what a triangle looks like. In the ordinary course of things, we actually wouldn't use it to model these types of effects for a variety of reasons that I can elaborate on if you'd like, but are outside the scope of this talk. Okay, so given that, we write down a model. Now, whereas before we only wrote it down for one tie at a time, now we're writing it down for the whole network at once, right? And we specify this model in terms of the statistics of the network. We call them sufficient statistics. They are functions of the network and maybe some actor attributes, right? And then we parameterize it by a vector theta of model parameters, and then we take a dot product, which is basically we take each element of theta and multiply it by the corresponding element of G. So each G represents some summary statistic of the network, and we multiply it by its corresponding theta, and then we add them all up, right? And then we exponentiate the result and divide it by the normalizing constant, which is often intractable, which is why we end up using MCMC to simulate and estimate these models. This is again, that's a whole separate talk, but the good news is that there are several fairly robust user-friendly software packages, including open source R package Ergom, which I maintain, that can be used to estimate this in a reasonably robust and user-friendly manner. Right, so what can we put in there? Well, we can put in to those models something like the density of the network, right? We can put in mixing matrices to model homophily or heterophily or whatever other kind of mixing patterns we have, and we can put in more than one mixing matrix at the same time. We can put in various degree distribution effects, how many individuals have no connections, how many individuals have one, how many have two, and so on. We can put in clustering or triadic or various cycle effects, high order stuff. We can put in things like distance effects. So, you know, what is the, to model propinquity. And the nice thing about this framework is because we have that one exponential with the dot product, all the effects are estimated and reproduced jointly. So how do we interpret these models? Well, there are two ways of interpreting. One is population level. In general, if you increase a particular element of theta, particular theta k, you will put more probability on networks with more of whatever g of k represents, or gk represents. Right? So if theta k corresponds to the number of edges, then that'll increase that. And I almost think of it as having a number of dials, one for each network feature. And you turn the dial to increase that feature or decrease that feature. It might also affect other features of the network, but you can adjust them down to get the configuration of features that you expect, that you want to see in expectation. There's also a dyad level. That is, there's a low-level interpretation as well. If we look at the probability of a relationship, given the rest of the network held fixed, right, because the relationships can't depend on each other, like a friend of a friend becomes a friend, but if a condition, it turns out that it kind of falls apart into this form, which is like theta 1 times the change in the network feature due to changing that one relationship, ij, that we're looking at, right, aj, and plus theta 2, same thing, G2, same thing, plus all the others, which gives us something that actually resembles logistic regression. So we can borrow a lot of what we understand about logistic regression to understand ergons. Okay, so how do we fit these? Well, again, there's a whole separate thing, but I'm going to focus on a particular kind of estimation from sampled network data, in particular egocentric sampled network data, because that's the kind of data that is the easiest to get. So in a perfect world, we would see something like this, right? We would see a nice network in a Petri dish, and we would see how everybody relates to everybody, and we can identify everybody. Of course, in real life, we don't often observe that. So this methodology was developed primarily in sexual partnership networks. Again, recall Sangines's talk, but and there you might not be able to identify a person and their partners, but you might be able to get some information about their demographics. The person might tell you like, hey, I'm a red. I don't know whether you can see the mouse cursor here, but I'm a red and I have a connection with one blue, and we can't tell which red this is in the network or which blue, or whether two of the reds are not talking about the same blue, but we do have this big picture demographic level information, right? Of course, we don't even get that. Usually we get a sample of individuals, of egos in the network. That's what's called an egocentric sample. But it turns out that we can actually get pretty far with that. Now, of course, there are other sampling methods, including link tracing. They have their own challenges. which I won't get into. So the interesting thing about these models, now remember how I called those G's sufficient statistics? Well, it turns out sufficient actually means something very important. And that's that we don't actually need to see the complete network to estimate the parameters of this model. We only need to see the sufficient statistics. And we can estimate those from the data. Now, how would we estimate them? Well, let's come back to this, our original egocentric sample. Well, we have our sample, and let's say we want to know how many red-blue ties there are, or blue-red. Well, we count 7 of them in the sample, but remember, but consider that every one of these relationships would get reported twice, once from each end, if we asked everybody in the network, right? So we divide it, we observe 7, we divide by 2. Then we multiply by the sampling weight, that is, we had 20 in the population, 10 in the sample, and so our sampling weight is 2. Now, similarly, if you want to have red and blue ties, or if you want to count the number of individuals who are isolated, who have no connections, although here we don't divide by 2 because we don't have double counting problem there, and other degree distribution effects, right? So even without actually being able to see the network, we can get a pretty good idea of the big picture network features of the sufficient statistics. So given those, that's all we need to get the estimate for the parameters. And in fact, we can even use various sampling machinery sampling theory machinery to quantify uncertainty. So here's the one application that I'm going to illustrate this on. This was for racial disparities of HIV in the US. This is a picture of annual incidence per 100,000 of heterosexually acquired HIV infections, right? And we can kind of see some patterns, right? We have differences, big differences by race. And also within each race, women have higher rates of heterosexually acquired infections. So we set out to try to explain that, and we took data that are egocentric like that, with demographic information about individuals and their race and the partners in their race and miscellaneous other information. And we can fit a number of models. These are ergon fits, which are fit on this very limited data that is egocentric but nationally representative. This is US National Health and Social Life Survey, the references at the top of the slide. And we can do things like test and represent the effect, the tendency to have same-sex ties versus opposite-sex ties. We can model activity by race, again, using whites as a baseline. We can see whether, there's a differential tendency to have ties. We can look at homophily, typo there. We can look at monogamy by sex and race, which again is one of those degree effects, right? And we can simulate, right? So in particular, we can use that to validate the model. And in this case, none of the models we fit actually have the full degree distribution in them. And yet we can look at how the models recover the degree distribution with the parts of the model, with the things that are in the model, right? Which is just monogamy. And it turns out that model 3, which is the one with the monogamy, is the only one that covers the degree distribution. Right? So that's one way of validating the model. Then we can also look at how we can then simulate and see how exposed different people are in the network. So in this case, this is the percent of individuals who are in a component of size greater than 2. That is, now component is basically the set of people who can be reached through the network. So a component of size 2 is just 2 people who are each other's partners and nobody else's. Now, a component of size greater than 2, that means that one of the people has another partner, at least one, and that means that both people in the component are exposed by the network. And it turns out that once we control for differences in tendency towards monogamy, we actually see a pattern that's quite semblant of the one that we see with the observed incidence, right? So what this general approach lets us do is to use this very low order data, like this very demographic level data, to fit a model that incorporates only this demographic level data, does everything jointly. Then through simulation, it lets us understand higher order network properties, right? So, and just as a brief postscript, there are dynamic extensions for this. Sam GNS talked about them, so I won't get into them right now, except that we might observe data like how long have 2 people been partners, right? So, this particular red has been with this blue for 2 weeks. right? Or this blue with this red for 4 years. And that lets us add additional statistics, sufficient statistics to the model. Well, again, I don't want to get into it in too much detail because I'm pressed for about 8 minutes, I think, or 6 minutes. So how does that relate to bipartite networks? Well, the thing is that so far we talked about HIV. HIV usually spreads person to person. COVID-19, SARS-CoV-2, it can spread person to person directly, but it can also spread from a person to a fomite to a person, or from a person to the air around the person to the person by sneezing and some such. More generally, from a person to a venue to a person. Now, this work, before I continue, this work is joined with Tim Churches and others at the UNSW Center for Big Data Research and Health. And they've asked me to plug this website where they have a friendly user interface for using what's called Shiny to be able to basically conveniently test various models for COVID-19 spread. Okay, so bipartite networks, how would we apply them here? How would we represent them? How would we represent these people and venues? Well, let's say we have this network. This is what a bipartite network looks like. You have people, several families and households, right? So that's actually one bipartite network. And then you have people going to work or to school every day, and maybe the adults go to work, the children go to school, and some of the adults also go to school as employees. And we can represent them using what's called an incidence matrix, where just it's a 1 if a given person is in a given venue and 0 otherwise. So this is for the houses, this is for the places of employment or education, right? What we can do with that is something called, we can take that bipartite network and actually look at it, convert it to a person-to-person network, right? Where we can look by basically, by what is really a matrix multiplication or projection, where we can look at which pairs of people have potentially encountered each other in a venue where they might have contaminated each other or infected each other, right? So if we have bipartite networks, we can model that aspect of COVID-19 spread. Okay, so how do we apply ergons to this? Well, it's actually quite straightforward because ergons are ridiculously flexible. For starters, we can restrict relationships to those between person and venue, right, to make the network bipartite. Then we have attributes of a person and attributes of a venue, and we can combine those to have predictors for a person visiting a particular venue. The framework allows us to constrain the number of venues for a given person or a number of people for a given venue. And as before, estimation requires only sufficient statistics. So just to think about something you might want to put into this model, and again, this is very preliminary work. For a person, you might have their location, occupation, age. For venue, you might have location, type of venue, size of the venue in physical area, and density of the venue in terms of how many people we'd expect in that venue for its size. And then given that, we can look at interactions and covariates, such as we take a person's location or residence and venue's location to get the geographic distance effect. We can look at and incidentally, if we look at a log of the geographic distance and put it in the model as a predictor, we actually get a power law distance effect, which is, again, the sort of thing that, for example, Stephen talked about the other day. Or similarly, we can look at age of a person or age category of person and type of venue to get the tendency to go to that venue, which is, again, a mixing matrix effect. And again, we can have any number of mixing matrices in the model at the same time. We can also look at different capacities a person might visit, such as school as a teacher, as a student, or shop as a buyer, as a clerk. Lastly, and I know I think I maybe need 3 more minutes. Is that okay? Okay. Lastly, a bit on estimation. How would we get sufficient statistics for this? Well, let's say we have a bipartite network like this, and we also have some distances here, right, between a person and the venue they go to. We don't get to see this network, right? Instead, if we get to see something more like this, so here we have a report from a person who goes to work 1 kilometer away, and a child who goes to school 0.5 kilometer away, and maybe a workspace that reports having 2 employees. right? But from that, we can already get quite a bit of information from this type of data, right? Because we know that there are 5 person to work, adult to factory connections. We know that if we add up all the distances, we end up with 6 kilometers worth of travel. We can do the same with adults in schools. We can do the same with children attending schools, and we can look at the distribution of the sizes of workplaces, right? And then beyond that, what we can do is we can look at, say, the intensity of participation. So if we have a person venue link, we can say control for the size of the venue to create weaker links there, or maybe different capacities of people attending the venue, or maybe model link intensity, which is actually pretty straightforward because we're conditioning on the present set of venue, which becomes a straightforward GLM. We can look at the interactions within the venue, such as a mixing of grades within school, workers in an office, which actually just becomes a one-mode ergon within venue, and we can use, say, polymod to model that. And so what we're working on now is incorporating and actually getting the data put together to construct this kind of model, and thinking about how to represent movements such as moving venues like buses, moving workplaces like cabs, and scaling and getting this to scale computationally, because the population of Australia is 25 million, and there are over 13 million valid addresses in Australia. So that's basically what I have so far about this. Thank you all these people, and this research is supported in part by all of these entities. And in case you're interested, just for the sake of recording, here's bibliography, and I try to sort it so that if you want to follow up on this, here's materials. Well, that's I think well, thank you all for coming to the talk.
Thanks very much for sticking to time too, Pavel. We have 5 minutes for questions. I don't have any in the chat as yet. So would anyone like to ask a question or comment?
Yes, I have one question. I guess that you simulate this by MCMC to kind of reach a stable distribution. Do you consider the trajectory of the MCMC once it is stable as a dynamical version of this model?
So that's a really good question, because there is work by, I think, Johan Koskinen, who is formerly at Manchester, now at Melbourne, who has worked with this framework they call ergons, or longitudinal ergons, which sort of consider that. I haven't worked with that particular approach, and I'm a little bit skeptical about it for a number of reasons that I'll be happy to talk about if you'd like, but it is in principle possible. Again, in practice, I prefer a somewhat different approach, which again, I think Sam Ginesse talked about it a bit with Sturgum's in his talk.
Okay, thank you.
Next question. I had a general sort of question, Pavel, that if you simulate networks in this sort of way, then you are going to get a network that in some sense fits with the data you've put in, but can there be aspects you're missing? Maybe difference between the overall thing being relatively geographically closely connected, or being more spatially spread out. I mean, this was a problem that I think Stephen Riley was trying to address earlier in the week.
So there is nothing stopping you from putting in propinquity effects, and again, you can put them on various scales to get various strengths of propinquity effects. But as a more general question, yes, it is important to check the goodness of fit of the model. Again, one way to do that is to look at, essentially to look at the features of the network that you did not explicitly put into the model, and see if your model is able to reproduce them, which again, we did with the degree distribution. We only modeled the number of monogamous individuals, but we also got the number of people with 2 partners, 3 partners, and so on for free. right? So that's one way to do it. As another way to think about it is that, and the one property that exponential family random graph models have, and this is a somewhat a technical term, is that they are what's called maximum entropy distributions. And that means that basically, given the things that you actually put into the model, they are as random as they can be. So in some sense, you're kind of covering the range, you're covering the best possible range, or the biggest possible range of what could happen given what's in the model. And in that sense, I think, and again, because they give you some notion of how much uncertainty there is, I think that helps. I mean, obviously it doesn't solve all the problems. All models are wrong, some are useful, but I think, but the maximum entropy property does help, I think.
John, you're muted.
Is that better?
Yes.
Thank you, Pavel. Just a question. If these are weighted networks, does everything go through just the same? Is it a trivial extension to apply these theories to weighted networks? Or is there a whole other dimension of complications that we need to be aware of?
Yes and no. So I have a whole separate books, several papers and several packages and several and even some workshops on how using ergms for valued data, how to use ergms for valued data. So the sampling and the inference machinery is unchanged. This is because ergms have this property that everything reduces to those summary statistics, right? But when you have valued data, basically you have to make a lot more choices when specifying those statistics, right? Even like, for example, how do you define triad closure bias when you have counts of relations rather than just presence or absence, right? And there are also a few other things you need to specify. But I guess, but the bottom line is that specifying the models can be more challenging. You have to think about more things, take more things into account, check for more problems, but the inferential machinery stays the same and transfers directly. And and the packages that I've mentioned, well, the ergm package has extensions for valued network data, although we don't have user-friendly interface for fitting Eurocentric data to it yet. If somebody wants to work on that, I'm happy to collaborate, by the way.
Would I know if I was doing it wrongly? I'm thinking of ecological networks, which I've worked on in the past. Okay. And we would just have a load of numbers in a matrix and randomize them, because that was the game that people were playing in those days.
Yeah.
And we would, sorry?
Like QAP, QAP? Oh,
I don't know.
Never mind.
Okay. And it took a lot of it took a lot of mistakes, a lot of staring to realize that there was a really simple structure within these networks, which we were completely ignoring in all of our off-the-shelf randomization schemes. And it just took actually very simple maths and staring at mistakes for ages to make it work. But I was wondering if there are warning signs for when your ergm is misrepresenting your data.
There are several. One is actually that it doesn't fit, that the model estimation algorithm doesn't converge. So there is a whole long history which you might have heard of called with ergm degeneracy. I suspect that's a word that people have heard around ergms, and there's a lot of history there, which again I don't think this is a good use of time to go through. But one symptom is that trying to use MCMC to fit the model doesn't work. But more generally, again, I think the easiest thing to do is well, actually the easiest thing to do is actually just look at the AICs and the BICs and all those things. And then, you know, if one model is better in that respect than another, then probably the other model doesn't fit as well. There's also a paper by Hunter et al. 2008 in Journal of American Statistical Association, which talks about how to basically simulate network features not in a model, and then look at how they match the observed network features, and thus get some idea of lack of fit. this is actually, one can also use that, by the way, to test for various additional effects in the model that you don't necessarily want to put into the model, but that's a whole separate, again, that's a whole separate conversation. The thing is, the exponential family framework is, in some ways, it can be hard, challenging to specify and fit, but it's also quite amazing because you basically get a lot of stuff for free. And I get it. So I know this is probably a broader answer than what you were looking for, but it is where it is.
I think we should probably move on to the next speaker. We're a couple of minutes over, and we have plenty of time for general discussion later on. So if you have other questions for Pavel, save them up for, or that you can ask them later. I hope Pavel will stay with us. Okay, so thank you very much for that.